Okay, let's do a buffer problem. And this time let's do a basic buffer problem. So we're going to write buffer example with weak base. And the base we're going to use is going to be NH3, which has a KB of 1.8 times 10 to the minus 5. It's ammonia, so we can do the example. This is going to be a long video, so pay attention, or you don't, it's going to take a while. So a base, basically, the model that we have for how a base works in water looks like this. I'm going to take this, and this makes, I'll just write the whole thing out first, and then we'll talk about it in just a second. So this is ammonia, which is a weak acid, or weak base, and you can see that from looking at the dissociation constant. The ammonia acts as a base by accepting the hydrogen from water, so it's a proton acceptor, so it's a base, and it also increases the amount of OH minus in solution, so it also behaves like an Arrhenius base. This is ammonium ion. Now, the general formula that we use when we look at this, we don't always write all these out. There are lots and lots of weak bases that are all have this nitrogen in them, because nitrogen has, if you recall, a lone pair of electrons, and that lone pair of electrons can grab one of the hydrogens from water, and so there are lots of amines that have basic properties. Among them amino acids, so the amine in an amino acid. The general formula, though, that we use is we say base, and then we say the conjugate acid is BH plus, and then plus OH minus. We write it this way because that avoids having to write this. And in this case, it's not that big a deal, but in some cases it can be really tedious and long. So we're going to have then a basic buffer using ammonia and the ammonium ion. And the way we would mix one like this, let's just make one really simple one. It has a two-component buffer. Let's say we take 50 cubic centimeters of 0.1 molar NH3, so that's an aqueous, of course. All right, so we have some dissolved ammonia, and we have this concentration, so 0.5. And if we want to, we can go all the way out and say, we can realize that this is, of course, going to be 5 millimoles of NH3 in solution. Just to make sure that we are clear about that. And then we take 50 cubic centimeters of 0.1 molar NH4Cl aqueous. Now, NH4Cl aqueous is actually that ammonium chloride, but the chlorine in this case, or the chloride ion, is basically just a spectator. So what we really are talking about is NH4 plus. And again, if we do the calculation, we can find that 50 times 0.1 is going to be 5 millimoles of NH4 plus. That's our amount. Now, for this particular problem, we're going to probably have to figure out exactly what the concentration is as well, because we can't solve it just by doing it with millimoles. But I'm going to save this for a later discussion. Now, we've already talked about how we know that the equilibrium constant, or the dissociation constant for this base is 1.8 times 10 to the minus 5. We should write up what that really means then, so we're real clear about that. So 1.8 times 10 to the minus 5 is the KB. So this is KB equals. And this is equal then to the products over the reactants in this equilibrium process. So we'll write it full on this time, and then so one of the products is obviously the ammonium ion. The other product is OH minus, and the reactant is, in this case, the base that is dissociating. Now, it's not actually dissociating, right? It's reacting with water. We do not include the concentration of water because its effect on the total concentration is very, very small. And we really can't talk about concentrations of water in water. But it doesn't change the volume significantly, so it doesn't actually change the concentration either in any regard. We can reformulate this, and this is how I will be using it, right, as BH plus concentration times OH minus concentration over the B concentration. It makes it a little bit simpler for us. So this is the way I'll be writing about it from now on. So if we're going to find the POH or the pH and the POH of this particular solution, this buffer, we then need to realize that we have to reach equilibrium. So we take our B, and it reaches equilibrium with BH plus OH minus, and we put it into the ice box, and we know that our initial conditions are, oh, wait a minute, we have to calculate our concentrations. So we need to go back up here and remember that we have 5 millimoles, and so the new constant, what's the total volume? So here's our moles, right, our mole, and here's what is our volume then? Well, our total volume is 100, and 100 here, right, because we've mixed these. So now we realize that this is 5 millimole over 100 cubic centimeters. So 5 divided by 0.05, and 5 millimole divided by 100 is equal to 0.05. So our initial concentrations of the two components of this buffer are the same. So we have base, it's going to be 0.05, and then we have the BH, 0.05. And we don't know this, and this is what we're going to try to find out. But we do know that the base is so strong, or strong enough, that it's going to dissociate or react, and it's going to decrease in amount by a slight. It's going to decrease in concentration slightly, and this is going to go up in concentration slightly, and then the OH is going to appear. So we have equilibrium concentration of 0.05 minus X, 0.05 plus X, and this is going to be X. We now want to put this into our equilibrium expression, this one right here, right? So we put it in there, and we realize that the BH plus concentration is 0.05 plus X, parentheses, times X over 0.05 minus X. And this should be equal to then 1.8 times 10 to the minus 5. Now, depending on how we approach this problem from this point, we realize that this X and this X, we have to think, is this X going to affect this concentration very significantly? Is this X going to affect this concentration significantly? And if the answer to that question is no, then what we basically have here is 0.05 over 0.05, which is basically then 1 over 1, right? Because if these don't count. So what we basically have is we have 1 times x equals 1.85 times 10 to the minus 5. Now, mathematically, you can actually show this. And so I'm going to switch the page here. I'm going to do a little bit of math for you just to show. This video is a little bit longer, so we're going to switch that out. I'm going to start on a new page here, and we can look at what the consequences of that previous equation are. So let's look at the equation real quick. We'll write it down. You see it there. Whoops, got some stuff there. If we look at it, we can see, okay, there it is. There's our expression. I can write it on the top of the page if we want. So here we have 0.05 plus x times x over 0.05 minus x is equal to 1.8 times 10 to the minus 5. Now if we rewrite this, we can see that we have, this is going to turn into, some algebra here. And we all love algebra. Ooh, yay. So I'm just going to rewrite it. Right, so I'm going to move the 0.5 minus x up onto this side. I flipped it over. I'd like to do that anyway. So there we have it. We have 1 point. We move this up, and it becomes this expression. And if we rewrite it then, and we do the math, we get something like this. And we can see that it's a quadratic. Right, 1.8 times 10 to the minus 5 times 0.05 becomes 9.0 times 10 to the minus 7, right? 5 times is just like that, halving it. So then we have 1.8 times 10 to the minus 5x, and then that's still the same way, but then I just distributed the x and you get this. So essentially then, what you're going to realize now is by looking at the next step, we're going to rewrite this. I'm going to rewrite this all on this side. So it's going to be, everything's going to be equal to 0. So 0 equals, so x squared plus, I'm going to combine terms here. I'm not going to do that step for you, but you can do it yourself if you want, right? Plus 4.998 times 10 to the minus 2x minus 9.0 times 10 to the minus 7. Now, if we look at this middle term here, the effect that this 1.8 times 10 to the minus 5 had on this original concentration, 0.05, even in this quadratic, is minimal. It went from 0.05 to 0.04998, so essentially 0.05, although it's in scientific notation. If we find the x's for these, we have two x's. One x is going to be 4.9998 times 10 to the minus 2, but it's a negative. It's interesting that those numbers are the same, almost. And then the second x is 1.800 times 10 to the minus 5. Look at that number. That number is exactly the same as our original KB, the dissociation constant of the base. If we continue with this calculation, then we'll do it in one direction here, right? We can use this x, right? x2, so x2, and that's essentially 1.8 times 10 to the minus 5. We can't use the negative one, right? Because if you take 0.05 minus a negative number, it increases, which is exactly the opposite of what we want to occur, or we know it doesn't occur. So we assume that this x is equal to the OH minus concentration, that x. We can then find the POH by taking the minus log of 1.8 times 10 to the minus 5, which is equal to 4.74. If we want to, we can continue and find the pH by taking the 14 minus 4.74 to give us the pH, which is 9.26. Notice, it's still basic. So the pH of this buffer is basic. Now, if we had continued from the previous page and skipped the quadratic, right? And just gone up to this original problem here and realized that, okay, these x's are not going to change these two values whatsoever. And we can see that that's basically true because this value is very, very small compared to those. So if these x's aren't going to change those values at all, we can then simplify this problem. And we can do it by using something called the Henderson-Hasselbalch equation for bases. So we just take the POH, we make it equal to pKb minus the log of NH3 concentration over NH4 plus concentration, which basically is just like saying POH is equal to pKb plus the log of the other way around, right? BH plus over B. And that's this rule of logs. Since this is the base and this is the BH plus, we're just flipping it. When you switch the sign on the log, it switches it inverts the fraction here. It doesn't matter in this case because when we look at our values up here, we see that the POH is going to be equal then to the minus log of 1.8 times 10 to the minus 5 plus the log of 0.05 over 0.05, which is the log of 1. And the log of 1 is 0. So this becomes exactly the same problem. So it becomes POH equals the minus log of 1.8 times 10 to the minus 5 plus the log of 1, which basically is equal to 4.74. Without doing the quadratic. So that's the answer to this particular base buffer. Now, of course, I'm going to do another problem in a few minutes, or in a while, that I'll post, where we change the relationship between these two by either adding a base or an acid.